All right, so we're going to start chapter 18, and the first section of chapter 18 is balancing redox reactions. So back in Chem 101, we did our favorite half reaction method for balancing redox reactions, which is admittedly a tedious way of balancing reactions, but it works out each time. And so that can make it really quite useful for us. And so the half reaction method, the whole idea is you can balance half of these redox reactions and put them back together and have an overall balanced reaction in a way that's easier than trying to do it all at one time. And so we're doing this because in redox chemistry, if you have a chemical reaction, it often takes place in what are called half cells, which is basically you have these two half reactions that are separated by a physical barrier of some sort, but they're connected via some things that we'll look at as we start to explore what an electrochemical cell is tomorrow. And so the way we're doing this is the half reaction method that you guys had done back, like I mentioned, in Chem 101. So hopefully you remember that. Hopefully you have some of your materials and it's not too much of a stretch for you to remember, okay? So the first thing we're always gonna do with redox reactions is make sure we're assigning oxidation numbers to all of the atoms and identifying the thing that's oxidized and the thing that's reduced. And using those tie lines and oil rig or Leo-Gur notation, whichever one you prefer to use, right? Or Leo-Gur, whichever you like, just make sure you're consistent. And we'll break the reaction apart into half reactions. We'll balance, then we'll balance the half reactions. To balance the half reactions, really the balancing of half reactions occurs in really 4 steps, right? So the first thing you're gonna do is balance everything other than oxygen and hydrogen. Then we're gonna balance hydrogen and oxygen, first off with oxygen, and then second with hydrogen. And the reason we wait to balance those is because these solutions generally take place in acidic or basic solutions. And even if they're neutral solutions, you still have both hydronium and hydroxide at your disposal, which we now know based on all the acid-base chemistry we've done. And then you balance the charges overall. Once you have the charges balanced, you can go and recombine the half reactions using basically there are 2 steps to do it, and then check to make sure your work is balanced. So basically, it's overall just a way of balancing these redox reactions. So when we assign oxidation numbers, what we'll do is for every atom in the chemical equation, we'll give it an oxidation number and calculate that. We'll then break that reaction apart into those half reactions. So we'll label them oxidation and reduction half reactions. When we balance in the next step all of the elements in the half reaction except for hydrogen and oxygen, we're just going to make sure that we have the equal numbers of elements in each half reaction besides oxygen and hydrogen, because we're going to be balancing those in subsequent steps. And so if you have 2 bromines in a compound on one side and 1 bromine in a compound on the other side, you need say 2 of the second compound, right? So that's pretty simple, straightforward way of doing it. Then when we balance oxygen, the way we're going to balance oxygen, right, is by adding water. Okay, so hopefully you guys remember that. We count up how many oxygens there are on either side of the half reaction, and then we're gonna say if there's a difference between those, we're gonna add water molecules so that we can balance out and make sure that difference is gone. Once we've done that, balancing hydrogen is done in 2 ways, and so this is sort of a simplified version. There are a bunch of different ways that you can actually phrase this. And I think I've sort of got it down to as simple of a way of doing this as we can get. So we're going to start out by balancing hydrogen by adding H+. But since we know from our acid-base chemistry that H+ is not actually meaningful in a chemical reaction, it's actually hydronium, we're going to convert it all to hydronium if it's an acidic solution, or we're going to convert it to water if it's a basic solution. And when we convert it to hydronium, we're going to do so by adding water. Now the water we add in this step is totally different from the water we added in step 4. And so you don't even count the waters from step 4 when you're doing this. You just, or you don't even take into account them as being added before. They're just already part of the reaction, essentially, is what I mean by that. And so you might have to add water to a side that already has water in it, and that's okay. If it's a basic solution, if it's a basic solution, you're going to be adding hydroxide. Okay, and if it's hydroxide, whenever you have hydroxide, right, so hydroxide plus H plus, right, that goes to make water automatically, very, very quickly. That's a strong base and a strong acid reacting, and so you can just put those two things together as H2O. And then we'll balance charges and use our least common multiple to balance out electrons. So we're going to go through that and sort of walk through an example. And one of the things we need for doing this is rules to assign oxidation numbers. Now, a lot of these rules you already have at your fingertips. You've used them before. Things like oxygen is going to be -2, fluorine is going to be -1. Fluorine's the most electronegative element, so you know it'll be -1. Oxygen will be -2 unless it's with fluorine, right? Because oxygen is the second most electronegative element. And so you can use a lot of the general electronegativity rules to balance oxidation numbers as well. But if you follow a list like the one here, you can easily balance oxidation numbers in any given chemical equation. And so we'll walk through that for the chemical reactions we're about to see. And so you can follow these rules. Things like elements have oxidation numbers of 0. Monoatomic ions have oxidation numbers equal to the charge of the ion. If you add up all of the oxidation numbers of a neutral compound, it's 0. The total charge should equal 0 if it's a neutral compound. But the sum of the oxidation numbers of a polyatomic ion is equal to the charge of the ion. And so using these rules and understanding, like alkali metals are +1, alkaline earth metals tend to be +2, unless you have that particular element is bonded to an element that's, has an electronegativity difference that would govern it in a different way. And so we can use our understanding of electronegativities in the course of this assigning of oxidation numbers as well, right? Remember, the more electronegative element wants the electrons in the bond, okay? So, but the general rules that we use, like oxygen is -2 and fluorine is -1, and all of those tend to come out of those electronegativity values, okay? So let's do an example for this, and this will be the only thing that we're really doing today is looking at this example for the balancing of a redox reaction, okay? So if we take our initial chemical reaction and we start to assign oxidation numbers, rules for hydrogen come first between hydrogen and nitrogen. So hydrogens will be +1. +1 times 4 gives you a total of +4. +4 means that nitrogen must be a negative. So the two nitrogens have to account for a -4 charge for this neutral compound. And so nitrogen, in order for those two nitrogens to account for a -4 charge, each nitrogen has to have an oxidation state, or oxidation number of -2. Oxygens, we know, here's our chlorate molecule. So oxygens we know are -2. So -2 times 3 means that oxygens account for a total of -6 charge. If oxygens are a -6 charge total, -6, so -6 plus whatever chlorine is equals the -1 charge on the ion. So chlorine must be a +5 here in the chlorate. Moving on to nitrogen monoxide, oxygen is a -2, so each nitrogen must be a +2. And then our chloride has, the chlorine is a -1 because that's the charge on our monoatomic ion, okay? So if we look at this now, we can see that the nitrogen changes its oxidation state and the chlorine changes its oxidation state, okay? Well, chlorine goes from +5 to -1, therefore it has gained electrons. In fact, if you're looking at that, right, each chlorine goes from +5 to -1, so you could almost make a note here that each chlorine has gained 6 electrons. If you look at the nitrogen, nitrogen goes from -2 to +2. So here it is losing electrons. Right, so loss of electrons is oxidation, right? And so this is stuff that should be familiar to you from chapter 4, the whole oxidation and reduction stuff. And hopefully you remember doing the balancing. Right? But in this case, if each nitrogen goes from a -2 to a +2, that means that each nitrogen has lost 4 electrons. Okay, and that's something, you don't have to do that, but it's kind of fun to take note of it because you can check that out a little bit later, okay? So if we look at our oxidation half reaction, all we're doing is taking the reactants and products that are associated with the oxidation, and so that's the N2H4 and the NO2. And the first thing we're going to do is put a 2 in front of the NO, okay? So that NO that has, you put the 2 in front of it to balance out the nitrogen. That's our first step in starting to balance these equations, these half reactions, is balancing everything except for oxygen and hydrogen. Okay, so you balance the nitrogen first, we put a 2 there. Then we've got to balance the oxygens. Well, from up here, we have no oxygens on the left-hand side and 2 oxygens on the right-hand side, which means we need to have 2 waters in this next step. So we add 2 waters to the side that doesn't have oxygen on it in the previous step. And so now we've balanced out oxygen, we balanced out our nitrogen, we need to balance out now our hydrogen. And the way we do that so the way we do that is actually, you'll see we have 4 hydrogens on the left side. So what we would do is put in 4 H plus on the right side to balance out those hydrogens, okay? And so the next step, why is this? Oh, sorry, I can't count. I'm missing, there's actually 8 hydrogens. So we need to put an 8 in there, not a 4. Honestly, I can count. So there's 8 hydrogens there. And so going from this step here to the next step, okay, we're gonna add some hydroxide molecule or ions, okay? And so the hydroxide ions, if you have 8 hydrogens here, right, what you're gonna do is you're gonna add 8 hydroxides to the right side and hydroxides to the left side. Okay, when you do that, the H pluses and the hydroxides on the right side, where anytime you have an H plus and an OH minus, they make waters. So you combine them into waters there. And on the other side, those hydroxides don't do anything, so they just stay as hydroxides. Then the next thing you can do is actually go and balance charges. So we have 8 minus charges, we have 2 neutral charges and another neutral charge, so a total of -8 on the left-hand side, and then we have a total of 0 on the right-hand side, so we put in 8 electrons on the right-hand side. And so that balances out our charges. And so we're going to leave it there, and we'll look at the reduction part before we come back to use our lowest common multiple as a way of balancing this. So the next step now is the chlorine. There's 1 chlorine on each side, so those are balanced. Then we've got our 3 oxygens. Okay, there's 3 oxygens there on the left side, none on the right, so we need to add 3 water molecules. Okay, and then to balance the hydrogen, we've got 3 times 2 is 6 hydrogens on the right and none on the left. For real, none on the left this time. So we're going to add in 6 H plus. Okay, and then when we do that, why am I missing something here? Okay, so when we have 6 H plus there, we should be adding 6 hydroxides to each side. Oh, I see why. Now, one of the things that's being done here is when you add that in, the hydroxides in 6 hydroxides and 6 H plus will give you 6 waters. But one of the things, if you choose to do it, is you can always simplify by knocking out waters on each side of the reaction. That's okay to do. And so this then becomes 3 waters, and that's why we have 3 waters here, and then no waters on the right side. So depending upon your preference for doing that, you can do it either as on the fly or like in the first example, just leave them in there until you're done. Either way is totally fine, okay? Then you're going to balance charges. So to balance charges, if you look at the right side, right, neutral waters, we've got -1 from the chlorate, -1 from the chloride, and 6 -1s from the hydroxide, for a total of 7 -1s on the right, and just 1 -1 on the left, which means we need to add 6 electrons to the left-hand side. So those are added in there. And then we've got 2 half reactions that are balanced in terms of charges. And so we can now use our lowest common multiple to figure out how many of each of those half reactions we need, right? And so we do that for the electrons. So 8 and 6 have the lowest common multiple of 24. And so we can multiply the oxidation, the balanced oxidation half reaction by 3 to get to 24. And we can multiply the reduction half reaction by 4 to get to 24. And so that the number of, I should do it from here, not there. My pen is not controlling it as well as I want to today. There we go. Get rid of that. Right, so we multiply that one by 4, we get to 24 electrons, right? And so when we do this, actually I'll change my colors here to say orange, okay? So when we do this, our electrons, when we add them together, those go away, 24 electrons go away, okay? Our hydroxides wind up canceling out. We have 24 on that side and 24 on this side. Try to make these clear. We have, so there are 6 waters here, and over here there's 24, so those 6 can go away. We're left with 18, and those 18 and the 12 will cancel out 6 more, so we can get rid of all 12 of those waters. We're going to be left with 6 waters, and that's what we will have here. And then we can plug in the rest of the pieces, right? The N2H4, the chlorates, the nitrogen monoxides, and the chlorides, and we put those and combine those together into the overall equation to get the balanced reaction. I know this is fast, and but the point is, it should be a review to you. And so I'm trying to not dwell on it and allow you to use the resources that you have in order to do this. And so I'm going to stop our recording here, and I'm going to show you some of the resources that you have on Canvas.